Okay, so thank you. Thank you for inviting me and allowing me to speak here. I'm also wearing multiple hats. I'm the Chief Science Officer of EBRAINS. I'm a Director of Research at Aix-Marseille University. And I've been invited in my capacity, in fact, as CSO of EBRAINS. EBRAINS is the European research infrastructure for digital neuroscience. It is a key deliverable of the Human Brain Project. The Human Brain Project being a huge investment of the European Union, effectively, 10 years of financing, about 640 million approximately euros over 10 years, with the mission to take an ICT approach, particular also brain computation through brain simulation approach towards better understanding of how the brain works, plus capacity to translate it in clinical applications and technological applications. And the Human Brain Project finishes now, essentially, in September. And EBRAINS has been placed on the European roadmap for research infrastructure, so it has been essentially rendered permanent. So it will accompany us for the decades to come, for the generations to come. And I'd like to give you an impression of what we're dealing with. First of all, it is supported by the European Union. There is an increasing number of full member states and also an increasing number of associate member states. What you're seeing here is old numbers. So at the moment, we are at about 50 to 60 partner institutions. And you see how it's distributed all across Europe. These academic service providers provide services. There are 5 supercomputers that are providing the hardware. There are storage facilities. There is a lot of software, effectively, being rendered available for the neuroscience community. The key idea here is it's not just another repository for data. It's not just another simulator that is being made available. The key idea is to render all these tools and data interoperable, which means, as you see here, so interoperability is at the core. There are data that are accessible, human data, animal data. You can put in your own data. You can put them in a context. Once they are integrated, you can access them in atlas services, going down on lowest resolutions. So there is a big brain atlas coming from Jülich, for instance. You can actually query individual regions of these atlases and link them directly on the parameters of models, allowing you then to parameterize the models and actually perform the simulations. You can analyze the subsequent data and perform validation and data analysis. This is not trivial, actually. When you look around at other infrastructures, I hear that quite often, actually. Yeah, we have this same thing. We have this integration with another tool and the data. If you look at this, it's always bilateral. This here is multilateral, allowing you to build uninterrupted scientific workflows in the domain of neurosciences. I want to give you some examples of where the additional information is coming in. What you see here is an example from epilepsy. In epilepsy, we spoke about this already. About 30% of all epilepsies are pharmaceutically resistant. So those patients, they have to be clinically explored in different ways. So you take the EEG, you make an MRI, and then you enter into the brain in order to perform a preclinical exploration. So, that you see represented here. The yellow balls are the SEEG electrodes that we have seen already multiple times, stereotactically, so in the volume and your register data. And based on this information, the clinician is making a decision about where the resection is to be performed, resecting the epileptogenic zone. What you can do now is you put it into a context, pretty much as Gustavo has spoken about earlier. You link it, you interoperate it with a full brain model, with a personalized full brain model. You extract the connectome, the connectivity between brain areas based on the brain imaging data of the patient. You reconstruct it. You can do this in very high resolution. You can actually then bias a parameter and perform some type of simulations. Yeah? And that allows you actually, as you see here, go way beyond the zone that is accessible by the imaging data. Yeah? And when you do this systematically, yeah, you see some of the statistics for retrospective data. On the left-hand side, you see the current clinical routine. This is a false discovery rate. The resections that have been performed. In green for seizure-free patients, in red for not seizure-free patients. There is actually no statistical difference. When you link it to the model, yeah, and you perform then inference, you can actually infer epileptogenic zones that are outside of the visible area, and it turns out that actually 30% of all the cases are outside of the accessible range. So what you're doing is you're unfolding the space through the model. Yeah? And the model is, at the end of the day, if you become a little more abstract, the model is a mathematical representation of our knowledge. Yeah? In anatomy, in physiology, and the patient-specific representations in terms of the personalized digital twin. When you connect that, you're capable of going further than you're able to do with the data alone. Yeah? And now try to, rather than talking about a spatial unfolding, think about an informational unfolding. Yeah? And to generalize this. And this is actually what we are doing. Yeah? And this has been done, for instance, in healthy aging populations. There is a Jülich cohort with about Jülich 1000 brains cohort, about 750 patients. There, it's impossible to predict cognitive performance for individual patients based on the structural or functional data, functional MRI data in this particular case. When you link it to the model, you can actually unfold the space and make individual predictions for cognitive performance. Or here, some other examples. On the top, multiple sclerosis. There is a clinical radiological paradox. That current standard, clinical standard in terms of multiple sclerosis, you try to find the lesions in the brain, but there is not a very good correlation between actually the severity of the disease on the one hand side and the total lesion load, as you see represented on the left. When you link it to a digital brain model and perform this workflow, yeah, so it can be generalized, perform this workflow, you can, for instance, estimate from the MEG data in the context of the model, the time delays via signal propagation along the individual fibers. And this correlates almost a factor 2, well, 60% better than the actually current existing standard. For this, you need to have techniques that are not just based on optimization, you need to go beyond that. You need to essentially find an equilibrium between, on the one hand side, the modeling tools, and on the other hand, the evidence that is in the data. Not just a simple naive optimization, but you actually need to sample this evidence because there are multimodal, sometimes there are multiple answers to the same question. If I ask you what is the square root of 4, and you tell me +2, you missed half of the solution. It's minus or +2. This you see represented here. These are empirical data spanning excitability in the case of epilepsy. In blue, the sampled, we call this Monte Carlo. Yeah? We sample the evidence in terms of probability distributions. And when you take a variational inference approach, in red represented, you're actually in between the modes that are possible. And in blue, you have two possibilities. For this one particular area, it's epileptogenic or not epileptogenic. You need to have this information. You need to take this in account. So this is critical. This you can do through interoperation. Another example, what you can do, because there was a lot of talk about stimulation here in the precedent talks, you can actually use the models now to navigate in the brain and develop novel technologies to perform better stimulation. Here's one example coming out of this process using multimodal temporal interference stimulation, which is a non-invasive technique where you're using actually the envelopes of high-frequency stimulations that allows you actually to go into the depth in the brain and actually focalize it through the multimodal frequency stimulation, and you can actually achieve the equivalent of deep brain stimulation following the navigation of the individual model. So these are things you can do once operating in an environment like this. And this has to be done essentially on a large infrastructure level because none of our laboratories has the capacity to do this independently. Modeling, mathematics, tools, supercomputing, all in an infrastructure integrated and rendered interoperable. This is the vision that is behind that. And the transition that we are making in this context is essentially a research culture from toolbox use towards a platform use where the tools are integrated. Thank you very much.